Okay, so I think we can begin. Our today's speaker is Professor Yuri Sachkov from Yaroslav Zalesky Institute of Program Systems, and he will tell us about Sub-Riemannian geometry of the group of motions. Yuri, you are welcome. Let's begin.
Thank you very much, Joseph, for your kind invitation and for possibility to speak here about the problem which I like. So I will speak about just one specific variational problem, which is quite simple when you state it, but the solution and the answer is quite complicated. I'm going to explain how it is solved and what is the answer. So this is a joint work with my former PhD student Andrei Ardentov and with foreign collaborators Gil Borley, Enrico Ledon, and Richard Montgomery. Okay, so let me start. First, I will describe the contents of this talk. First of all, of course, I will state the problem precisely, and then the talk will consist of two parts: the old one and the old story, and the new story. The old story contains results which are obtained roughly 10 years ago. They are in items from 2 to 4. So I will describe geodesics of the problem, will describe the local and global optimality, and describe the principal characteristics of the Sub-Riemannian problem, that is the cut time, cut locus, and spheres. And then I will tell you the new story, a remarkable relation of this Sub-Riemannian geometry with the so-called bicycle geometry. I will state the bicycle model of this problem and describe its connection with remarkable curves called Euler elastica, and describe so-called infinite geodesics in the problem. Then I will pass to a description of isometries, homogeneous and equioptimal geodesics. And finally, in item 7, I will tell something about application of this problem to anthropomorphic curve restoration. So let me start from the problem statement. Consider a very simple model of a car in the plane. It is just a vector. It is just a vector. And it is characterized by three numbers. X and Y describe the origin of the vector, and theta describe its orientation in the plane. So the state is a three tuple X, Y, and theta. Our car can move in the plane forward and backward, and it can rotate simultaneously. We are given initial state of the car Q0 and terminal state of the car Q1, and we should move the car from the initial state to the terminal state in an optimal way. Optimality means with respect means with minimum length. The length is measured in a natural way. It is length in the space of positions and orientation in the space x, y, theta. Of course, if we measure the length in the space x, y, then the motion would be trivial. We should rotate. We should rotate, move along a straight line, and then we should rotate once more. This is quite simple and not very natural. And this length function is quite natural, so we measure length with respect to positions x, y, and orientation theta. Alpha square is a scale parameter, but mathematically speaking, we can set it equal to 1 by rescaling x and y. So this is our roughly this is our problem statement. I will speak about this one particular variational problem. So as you see, it is quite simple to state, but the solution is rather complicated. In order to find a solution that is an optimal trajectory of the car, you should solve systems of equations in Jacobi elliptic functions, and I am going to describe this. So let us state this mechanical problem as an optimal control problem. The first three equations describe dynamics of the system, or maybe better, kinematics of the system. So the car can move forward with linear velocity u in direction theta. So this gives us two first equations, and it can rotate around itself simultaneously. So u and v are controls. They are functions of time which we can choose arbitrarily. So this is dynamics. This is a control system. The state is 3 tuple x, y, theta, x, y in R2 and theta in this circle S1. So our state space is R2 times S1 is this three-dimensional manifold. Control is two-dimensional. U and V are controls, as I have said. We have fixed initial state Q0 and terminal state Q1. And we should minimize this length. It is exactly the length which was before, but it is expressed in terms of control U and V. So this is exactly our problem, but stated in optimal control terms. Great. What can we say from the very beginning? There are obvious continuous symmetries of the problem, rotations and translations. If we have an optimal motion of a car, we can rotate it, and then we obtain once more an optimal motion. And moreover, we can translate it in the plane, obviously. So we have a rather big group of symmetries, a group of rotations and translations. That is why our problem is stated as a left invariant problem on the group of motions of the plane, or on the group of rotor translations. This group is denoted as SE2. It is the same direct product of R2 with SO2. R2 are translations and SO2 are rotations. This group is represented by a matrix of order 3 of this form. Here XY is vector of translation and theta is angle of rotation. So we have this three-dimensional Lie group, and we have the following left invariant frame of this Lie group consisting of 3 vector fields x1, x2, and x3. They have simple mechanical meaning. x1 means motion forward in direction theta, x2 means rotation around itself, and x3 is the Lie bracket. It gives us the motion of the car in the forbidden direction. When the car has direction theta, then x3 gives us motion in the right hand side, which is infinitesimally forbidden. So this is our left invariant frame. Great. And our optimal control problem is in fact a left invariant Sub-Riemannian problem on the group SE2. What does this mean? The dynamics of the system is written in the vector form in this form. Q dot is equal to U x1 plus V x2, where U is linear velocity, x1 is vector field of motion forward, V is angular velocity, and x2 is vector field of rotation around itself. The state is in the Lie group SE2, and control is two-dimensional and unbounded. We have fixed initial state Q0, terminal state Q1, and we have to minimize this functional. But this is exactly a length minimization problem for the following Sub-Riemannian structure on SE2. I recall that a Sub-Riemannian structure is a pair that consists of a distribution and a scalar product in this distribution. So we have the distribution delta, which is spanned by vector fields x1 and x2. You see that due to our control system, we can move at each point in a direction that belongs to the plane spanned by x1, x2. So we have this distribution delta, and in this distribution we choose the scalar product, which says that x1 and x2 are orthonormal. Then L is exactly the Sub-Riemannian length functional. So we have a left invariant Sub-Riemannian problem on the group SE2, and it is known that such a Sub-Riemannian structure is unique on the group SE2 up to local isometries. And this is a picture. We have fixed initial state Q0, terminal state Q1. We should find the shortest curve such that at each point the curve should be tangent to our plane of distribution. This is a picture of our Sub-Riemannian problem, in fact, of arbitrary Sub-Riemannian problem. Great. Now, I would like to recall what is known in this domain. What is known about three-dimensional Sub-Riemannian problems. First of all, there is a basic three-dimensional Sub-Riemannian problem on the Heisenberg group, which is the simplest Sub-Riemannian group. This problem was studied by Verchik and Gershkovich in 80s. This is a left invariant Sub-Riemannian problem on a particular Lie group of the Heisenberg group. Then there was a study of generic contact Sub-Riemannian problems in R3 due to Andrei Grachov and Jean-Paul Gaultier in 1996. And moreover, there are several other models which were studied completely. The flat Martinet case and several left invariant problems on SO3, SU2, SL2. The problem on SE2 about which I will tell you today. One more problem on SH2, group of hyperbolic motions of the plane. And that's all. There are just a few left invariant models on three-dimensional Lie groups which were studied completely. And all the rest contact left invariant 3D Sub-Riemannian structure are not studied because they're integrable in elliptic integrals of the third kind, which are very hard to deal with. So our problem on SE2, which is in this list, and I'm going to describe what is known about this problem. So first of all, existence of solutions. So given 2 points Q0 and Q1, whether there exists a curve which gives us the minimum to the length functional. There are general results which say that there is existence of solutions. First of all, we have a control system that is linear in controls. So we can move in direction x1 and x2, and whether it is possible to move arbitrarily in the group, so whether the system is completely controllable. This is decided by Rashevsky-Chow theorem. We have to compute Lie brackets of vector fields in the right-hand side. So we add to x1 and x2 just one Lie bracket of x1 and x2, and we obtain the tangent space to the Lie group. And then Rashevsky-Chow theorem says the system is completely controllable. That is, any 2 points in the group are connected by a trajectory of the system. And then there is another general result, Filippov's theorem, which says that there exist minimizers. So for any pair of points Q0 and Q1, there exists a minimizer that connects them. So with the existence of solutions, everything is simple. It is solved in via general theory. Great. So now I'm going to describe how these minimizers can be found. There is a general necessary optimality condition in optimal control called Pontryagin maximum principle. It is a necessary optimality condition in the following sense. If a trajectory is a minimizer, then it satisfies certain conditions. I am not going to describe them in detail here because it is rather complicated, but I will tell you the answer. So what does Pontryagin maximum principle say? In general, there are optimal trajectories of 2 types: abnormal ones and normal ones. In this case, abnormal trajectories are very simple; they are constant. So this is trivial. So the main attention will be paid to normal, so-called normal extremals. And Pontryagin maximum principle says, in the normal case, the following: if we have an optimal trajectory, then it is a projection of a Hamiltonian lift. So we should pass from the state space to the cotangent bundle. In the cotangent bundle, we have a Hamiltonian vector field, and for each optimal trajectory, there is a trajectory of the Hamiltonian vector field upstairs, which is projected down to the optimal trajectory. So we should pass from the state space x1 theta to the cotangent bundle. So we should add so-called adjoint variables. And in this case of a Sub-Riemannian problem on SE2, this equation for adjoint variables is this: gamma dot is equal to c, c dot equal to minus sine gamma. We have here only 2 equations because we can restrict ourselves to the level surface of the Hamiltonian, because we can reparameterize trajectories by arc length. So for adjoint variables, we have this equation of pendulum. very well-known equation of pendulum. And downstairs, we have these three equations for x, y, and theta. It is well known that equation of pendulum is integrable in Jacobi's elliptic functions. We can integrate it, and then we can go downstairs and integrate equations for x, y, and theta. This was done, so the whole system of differential equations, the whole Hamiltonian system for optimal trajectories is integrable in Jacobi's elliptic functions.
Yuri, I'm sorry.
Yes.
I don't understand notation. What does this 2s1 gamma, what does it mean?
Well, S1 gamma means R modulo 2 pi z. And 2s1 gamma denotes the double covering of the standard circle. So it is R modulo 4 pi z. So gamma takes values in the segment from 0 to 4 pi.
I see. Thank you.
The reason of this is that here in the equation you see gamma divided by 2. Roughly speaking, this is the reason why gamma takes values from 0 to 4 pi. Okay. So we have these equations, they're integrable in Jacobi's functions, and as everybody knows, there are different qualitative types of trajectories of the pendulum depending upon its energy, and this will be crucial for us. I will recall this. So, let me stress this notation. So we have a cylinder C capital, which is a double circle multiplied by a line. So this is a cylinder where lives the pendulum. So gamma C small lives in the pendulum C capital. This will be very important for us. This is the phase cylinder of the pendulum. And now I will recall the stratification of the phase cylinder of the pendulum C capital. You see C, the vertical line is just a real line, and the horizontal axis gamma takes values from minus pi to 3 pi. So this is a double covering of the standard pendulum. So we have the energy integral. This is kinetic energy, c squared divided by 2, and this is potential energy. It takes the total energy takes values from -1 to plus infinity, and the phase cylinder of the pendulum stratifies into stratas corresponding to different values of the energy. If energy is small, if energy is from -1 to 1, this is C1, then the pendulum oscillates here or here. This is C1. C2 gives us domain where energy is big. So in this case, a pendulum rotates in one direction here or in another direction here. C3 is the critical level of energy. The energy is equal to 1. So then the pendulum moves along a separatrix, and it tends to a non-stable equilibrium for infinite time. C4, when energy is equal to the minimum value -1, it is a stable equilibrium of pendulum. It is a center. And C5 finally is a non-stable equilibrium when energy is equal to 1 and C equal to 0. It is here. So it is a saddle point of the pendulum. So we have different trajectories of the pendulum depending upon its energy. Great, and depending upon this stratification, we obtained different parameterization of geodesics. If we a geodesic is a curve whose sufficiently short segments are optimal. Big segments can be not optimal, but short are optimal. For example, to recall your intuition, if we have a Riemannian problem on the two-dimensional space, on the two-dimensional sphere, then geodesics are meridians which are passed infinite number of times, but they are minimizers only from the North Pole to the South Pole. That's all. So before describing optimal trajectories, minimizers, we describe geodesics. So what is parameterization of geodesics? If the pendulum oscillates with low energy, we obtain one set of formulas. You see that here appears Jacobi amplitude and Jacobi elliptic function Cn, Dn, Sn, and Jacobi epsilon function. If the pendulum rotates with big energy, we obtain another set of functions, also Jacobi elliptic functions. And in the degenerate cases, C3, C4, and C5, we obtain elementary functions, hyperbolic and linear functions, which parameterize motions of our car in the plane. So this was done, and these are the pictures. If the pendulum oscillates with low energy in C1, then the car moves in this way, so forward, looking forward here, it looks forward here, and then it looks backward here. And then this repeats infinite number of times. In C2, when the pendulum rotates with big energy, the car moves forward here, then backward here, forward here, backward here, etc. So these curves have cusp points. So these are projections of geodesics in the plane XY. These are trajectories of the car. They have cusp points. You see cusp points here and cusp points here. And in C2, there are also inflection points. While in C1, there are no inflection points. These arcs are convex. So these are generic geodesics. And in special case, we have the following pictures. If the pendulum moves along a separatrix, then the car moves along a tractrix. So this is a curve with just one cusp point, and with one vertical asymptote, or if the car rotates around itself in one or other direction, or finally the car can, of course, can move forward and backward. In fact, the last two cases are one parameter subgroups in our Lie group SE2. So these are all geodesics. This was described, but this is just a beginning of the picture, because these are only critical trajectories, and I'm going to find the minima. In general, the ideology of optimal control is similar to the ideology of calculus, as we know from the first year calculus, how we solve the minimization problems. We find critical points where derivative is equal to 0, and then we apply second order optimality conditions. We compute the second derivative and find the true minima. This ideology is applied in optimal control, with only difference that here the problems are infinite dimensional, but the whole ideology is similar. So just now we have described the critical points, that is geodesics, and now I'm going to describe how the minimizers were described. So now we pass to the question of optimality of geodesics. We should distinguish local and global optimality, which is quite natural. A geodesic Q of t is called locally optimal if for any epsilon there exists an arc length parameterized trajectory Q tilde that is close to Q in the uniform topology and has the same endpoints, and then that the time of motion for Q tilde should not be less than T1. So Q is optimal with respect to all other trajectories that are close in uniform topology with the same endpoint. And Q tilde, Q of t is called globally optimal if it is the best among any trajectories with the same endpoints, which is quite natural. Okay, now what are the reasons for the loss of optimality? There is a general condition called the Strong-Legendre condition, which originates from the calculus of variation, which says the following: is the second derivative of the this is the Hamiltonian of the Pontryagin maximum principle. If the second derivative is negative, then the short arcs of trajectories are optimal. This condition is satisfied. So all extremal trajectories that were found from Pontryagin maximum principle are indeed geodesics. Their short arcs are optimal. Now, how long can be these arcs where the optimality is preserved? In order to describe this, we need the notion of the cut time, one of the very important notions of Sub-Riemannian geometry and optimal control. Cut time. Cut time along geodesic is the following one. It is a maximum time t until which geodesic Q of S remains optimal. So we take the maximum time t until which geodesic is optimal. After time t, it is normal optimal. So this is the cut time, and in fact, to describe a solution of an optimal control problem, you should do two things. First, describe its geodesics starting at a fixed point, and then describe the cut time. So along each geodesic, you should describe the cut time. If we know this, in fact, then we know the solution of the problem. So the cut time is the crucial thing to understand. So what are the reasons for the cut time? What are the reasons for the loss of optimality? The first reason is called a Maxwell point. A point Q of t is called Maxwell point if the following condition is satisfied. If there exists another geodesic QS tilde that is different from QS, and if it comes to the same point QT at the same instant of time. So this is a picture. Q0 is the initial point. This is our geodesic. And suppose that we have another geodesic that comes to the same point with the same time t. Then this is a Maxwell point. It is known that after a Maxwell point, after just under some mild conditions, after each Maxwell point, a geodesic cannot be optimal. In the following sense, that there exists another geodesic that is shorter, Q hat, and it is shorter. The time T2 for Q hat is strictly less than the time T1. So the Maxwell point is the first reason for the loss of optimality. The second reason for loss of optimality is called a conjugate point. A point Q of t is called a conjugate point if it belongs to the envelope of the family of geodesics. So once more, this is our initial point, and we have a family of geodesics starting from Q0. And suppose that we have an envelope to this family, so that geodesics are locally reflecting in this manifold. Then this point Q of t is called a conjugate point. And it is known that after a conjugate point, a geodesic cannot be optimal. Just geometrically speaking, if it is reflected in the envelope, then there is another geodesic, this one, that is shorter. So after a conjugate point, a geodesic cannot be optimal. And we have the following general result. The cut time is equal to minimum of two times, the Maxwell time and the conjugate time. So if we know all Maxwell times and all conjugate times, then we can take minimum, and this is the cut time. The only problem is that typically it's very hard to know all these things. And now I will describe how this problem is solved. So first about the Maxwell points. What can be the reasons for Maxwell points? The reasons can be symmetries of the problem. Suppose that in the state space we have a symmetry, for example, a reflection in a certain codimension one submanifold. Then if a trajectory, if a geodesic comes to the mirror of the symmetry, then there is another that comes at the same point with the same time. Then we have obtained a Maxwell point. So the first thing to do here is to find symmetries of the problem. And it is very natural to start from the symmetries of the equation for adjoint variables for the pendulum equation. So we have the equation of pendulum, gamma double dot is equal to minus sine of gamma, and it lives in the double covering of the standard cylinder of the pendulum, this one, and symmetries of this equation of pendulum are quite visible. They are Z2 times Z2 times Z2. Geometrically, these are reflection. Epsilon 1 is reflection in axis gamma. Epsilon 2, which maps delta into delta 2, is a reflection in the axis C. Then reflection in the origin, which maps delta to delta 3. And then there is a translation from delta to delta 4, etc. So we have a group of 8 symmetries, Z2 to the power 3. These are discrete symmetries of our pendulum. Then we continue these symmetries from the adjoint equations, from the equation of pendulum to the equation of for variables x, y. And these continued reflections have quite simple geometric meaning. Epsilon 1 and epsilon 2, that are reflections in the axis, have the following meaning. Take this geodesic and reflect it in the middle perpendicular to the chord and obtain this dashed geodesic. This is definition of epsilon 1 and epsilon 2 modular rotation. We should add some rotation, but modular rotation, epsilon 1 and epsilon 2 are reflections in the middle perpendicular to the chord of the geodesic. Then epsilon 4 and epsilon 7 are just reflections in the chord of the geodesic. This is initial trajectory, and dashed is reflected, plus some rotations. And finally, epsilon 5 and epsilon 6 are reflections in the midpoint of the chord of geodesic. This was initial one, and this is the reflected, plus some rotations. So we have continued reflections from the pendulum to the plane x, y, and theta as well. This was done, and then we could find so-called Maxwell points corresponding to reflections. These are points where these are points to which two different geodesics come, and these geodesics are obtained one from another by these reflections. So on each geodesic and for each reflection epsilon I, we found infinite number of times T1, T2, etc. So at each geodesic, for each reflection, we found a countable number of Maxwell points corresponding to reflections. This was done, and of course we are interested in the first Maxwell time. So we found their minimum, and this minimum is called the so-called symmetric Maxwell symmetric first Maxwell time. So we have obtained the following upper bound of cut time. The cut time is not greater than the symmetric Maxwell time. This is the plot of this symmetric Maxwell time as a function of the energy. Energy takes values from -1 to plus infinity. Here are oscillations of pendulum with small energy. There is a vertical asymptote when the pendulum moves along a separatrix, and here the pendulum rotates in one direction or another. So this function, the symmetric Maxwell time, was described. This it will be important in the following. So now I am going to show that this symmetric Maxwell time is in fact the cut time. This is done by the study of the one more important notion of exponential mapping and conjugate points. once more. So the exponential mapping is the following one. It maps the pair lambda t, where lambda are adjoint variables gamma c. The exponential mapping maps this triple into the terminal point of geodesic q of t. So the exponential mapping maps this three-dimensional manifold, two-dimensional cylinder times R2 into our Lie group M. So this mapping from 3 to 3 variables, and a point Q is called is a conjugate point if and only if it is a critical value of the exponential. That is, if is differential is degenerate. And along each geodesic, we are interested in finding the first conjugate time. The first conjugate time is the minimum time when the Q of t is conjugate. So this is important for us because the first conjugate time gives us the upper bound of the cut time. Okay. And we obtained the bounds of the first conjugate time. If we obtain the following theorem. If trajectories do not contain inflection points, then there are no conjugate times. So the first conjugate time is equal to plus infinity. And if a trajectory contains inflection points, so that when a pendulum rotates, then the first conjugate time was bounded from below and from above by Maxwell times. What is important is that here the first conjugate time is not less than the symmetric Maxwell time. So we obtain as a corollary the following statement: the first conjugate time is not less than the symmetric Maxwell time. Great. Then we describe the global structure of the exponential mapping. What does this picture say? So in the right hand side, we consider the solid torus. The solid torus is the group SE2. SE2 is a three-dimensional group with coordinates x, y, theta. The plane xy can be described as a disk, so as an open disk. So this open disk is xy, and the angle theta takes value in this circle. So we have here a direct product of R2 with S1, so it is a solid torus. So in the right hand side, we have our Lie group SE2. And in the left hand side, we obtain, we have drawn the preimage of the exponential mapping. This preimage, what does it mean? In the vertical axis is axis of time, and the horizontal plane is the cylinder of the pendulum. And we have a double covering of the cylinder of the pendulum, and it is moved, it is mapped by exponential mapping to this solid torus. And what do we have in this solid torus? This solid torus is divided, is cut by 4 surfaces, by 2 disks. These disks theta equal to 0 and theta equal to pi, and 2 Möbius strips. So we have 4 surfaces, and they divide the solid torus into 8 domains. Great. In the preimage of the exponential mapping, we also have 8 domains. The preimage is cut into 8 domains by Maxwell points in the preimage of the exponential mapping. And we have proved that the exponential mapping is a global diffeomorphism when it is restricted to these 8 domains. So in these 8 domains, it is a diffeomorphism. It is one-to-one, smooth, and the inverse is also one-to-one. This was done. And on the basis of this result, we finally proved the expression for the cut time. It was proved that the cut time is equal to the first symmetric Maxwell time. And it has different expressions for different types of motion of the pendulum. If the pendulum oscillates, then the cut time is equal to 1/2 of the period of the pendulum. It is quite simple. So look at the picture in the left. So the period of the pendulum consists of two such arcs, one and second. And this picture shows you the cut time, which is half of the period. If the pendulum rotates, then the expression for the cut time is much more complicated. It is equal to 2k multiplied by p11 of k, where p11 is the following function. It is the first positive root of this equation in Jacobi's elliptic functions. So it was proved that this equation has always has a root for any k small, and bounds for this root were obtained. If pendulum moves along a separatrix, or it stays in unstable equilibrium, then the cut time is equal to plus infinity. This will be important further. So if once more, if a car in the plane, what does it mean for the car in the plane? If a car in the plane moves along a straight line, this is C5, of course, it is optimal up to infinity. And another motion that is optimal up to infinity is a tractrice. So if a pendulum moves along a separatrix, then xy is a tractrix, and it is also optimal up to infinity. And finally, if the car rotates around itself, then the motion is optimal until time pi. So this is the right picture. If the car rotates to one, if the car rotates counterclockwise or clockwise, then the motion is optimal up to time pi. So in for some motions of the pendulum, the cut time is expressed in geometrically visible terms, but in some cases it is not. Generically, you have to solve equations in Jacobi elliptic functions in order to describe the cut time. Okay, this was done, and now one interesting remark about so-called infinite geodesics. Definition: a geodesic Q of t, where time t is from R, is called an infinite geodesic if any its subarc restriction to any segment from A to B is a minimizer. And for our Sub-Riemannian problem on SE2, we are able to describe infinite geodesics. A geodesic is an infinite geodesic if and only if its projection to the plane xy is either a line or a tractrix. So this we have already known. If you go back, you see that the cut time is plus infinity, and this exactly shows you the infinite geodesics, the geodesics that are infinite, that are optimal up to infinity. So this interesting object was also described. Great. Now some pictures. This picture of a solid torus, where you have to identify the upper plane theta equal to pi with the lower plane theta equal to minus pi. So this plane should be glued. So and the cut locus is the following. You take all geodesics starting from initial point, and on each geodesic you plot a cut point. And the set which is obtained in such a way is called the cut locus. So cut locus is a very important notion in Sub-Riemannian geometry. It gives you the set of points until which geodesics are optimal. When they hit cut locus, they stop to be optimal. So the global description of cut locus is one of the goals in Sub-Riemannian geometry. So this is initial point. The cut locus consists of two paths. Local one, the local one which is adjacent to the initial point. So the initial point is in the closure of the local component, and the global one which is just the plane theta equal to pi. So this global description of the cut locus, and here is the same in the solid torus. So this initial point, this is the global component theta equal to pi. The car hits this plane when it rotates into one direction by angle pi or to other direction, and this is the local component of the cut locus, which is a part of one of the two Möbius strips. Recall that there were two Möbius strips, and one Möbius strip gives you the cut locus, some non-trivial part of the Möbius strip, which is shown here, is the local component of the cut locus. So this was described. Now, in some situations, minimizers were described. Of course, if a car moves forward or backward, this gives you a one parameter subgroup corresponding to vector field x1. Of course, it is a minimizer. Then, if a car rotates, as we have said already, rotates in counterclockwise or clockwise, then we obtain a minimizer up to time t equal to pi. This is also a one parameter subgroup corresponding to vector field x2. X2, recall, it is rotation. Now, once more, two more examples of minimizers. If a car stays here and it should move here, then it can move along this curve or along this curve. They both are minimizers. This gives you example of a Maxwell point when two different minimizers come to the same point with the same time. Two more examples. If a car stays here and it should move here, then it should move first forward, then backward, and then forward. And another trajectory with the same boundary condition. The car should first move backward, then forward, and then backward. This is also example of Maxwell point. This we have. But these are examples only for quite special boundary conditions. For generic boundary conditions, we have no other choice but to solve equations in Jacobi's functions. This can be done by some software. My students design software in Wolfram Mathematica for solving systems of equations in Jacobi's functions, and for arbitrary boundary points, it is possible to compute the optimal trajectories. So in such a way, so-called optimal synthesis was found. So for optimal synthesis is the following: given 2 points in the state space, we should know an optimal trajectory for these 2 points. So optimal synthesis on of the Sub-Riemannian problem on SE2 was described and computed. Okay, this was done. And several more pictures. This picture shows you the first Sub-Riemannian caustic. That is, you take arbitrary point lambda in the cylinder. This is gamma c in the cylinder, and take the first conjugate time, and take the corresponding point in the state space. So along each geodesic, you draw the first conjugate point. And this set is called the first Sub-Riemannian caustic. So this is initial point, and this is a picture of the first caustic. What can we say about spheres? If we have a Sub-Riemannian structure, then the manifold turns out to be a metric space. And as usual, in the metric space, you can define spheres. So what can we say about spheres on SE2? If radius is equal to 0, of course, sphere is just initial point. If radius is from 0 to pi, then the sphere is topologically equivalent to S2. If radius is equal to pi, then the sphere is equal to S2 with north and south poles identified. So the sphere kisses itself. And if radius is greater than pi, then the sphere is topologically equivalent to the two-dimensional torus. These are the pictures. The picture in the left gives you the sphere of small radius, of radius less than pi. it is topologically two-dimensional sphere, but only topologically, it is not diffeomorphic to the two-dimensional sphere. You see here are singularities of the sphere. If radius is equal to pi, then the sphere kisses itself at one point, and you can see here singularities. They are even more visible. And if radius is greater than pi, then topologically it is torus, of course, with singularities. So the spheres were described, and that's the end of the old story. So to summarize, we considered an optimal control problem, and we described geodesics, and along with geodesic, we described the cut time. That is the time when the geodesic loses its optimality. And we described the cut locus and spheres. So in a sense, this is a rather complete study of the optimal control problem, or of the Sub-Riemannian problem. And now starts a new story. Quite recently, just last year, we found out about a relation of this Sub-Riemannian geometry with so-called bicycle geometry. What is it about? Consider a model of a bicycle in the plane, a bicycle of length L. F is the forward wheel, and B is the back wheel. Of course, the front wheel can rotate, and we should trace the trajectories of the front wheel, which is in blue, and trajectories of the back wheel, which is in red. Of course, the trajectory of the back wheel is tangent to the back wheel, and trajectory of the forward wheel is tangent to the forward wheel. What is the configuration state of this system? We have 2 points B and F in R2, so we have pair BF in R4, where the distance between this point is equal to L. And we take L is equal to 1 by rescaling. This can always be done. So the distance between F and B is equal to 1. This is topologically R2 times S1, which is, as we know, SE2. What are the restrictions on motion of on velocities of the points B and F? The point B at each point should move in the direction given by a vector from B to F. This is given by this equation. B dot should be collinear with the vector F minus B. So this is the no-skid condition, отсутствие заноса, no-skid condition. And the question is, what are the shortest paths of the front wheel F of the bicycle? This is the question. This problem statement can be understood also on other kinematic models. For example, a car-like robot with a trailer. So this is a car-like robot, and it is connected with a trailer. So another model, a car-like robot with 2 driving wheels. You see here 2 driving wheels and a spherical wheels here. This car-like robot also models our bicycle, and even a rickshaw. Rickshaw also gives you an illustration to our bicycle. Rickshaw is the front wheel, and its car is a back wheel. So what problem can we state for this bicycle? This what is first of all, what is the state? The state is a triple X F Y F. So this is the front wheel, and theta B. Theta B is orientation of the back wheel. So the state is R2 times S1. What is the kinematics? The front wheel can move arbitrarily in arbitrary direction. So xf dot is equal to u1, yf dot is equal to u2. u1 and u2 are arbitrary, and there is a no skid condition, which gives you, after some simple computation, this equation. So we have a control system on R2 times S1 with controls U1 and U2, which are arbitrary and unbounded. We have fixed boundary conditions, QF0, QF1, and we are interested in trajectories of the bicycle that minimize the length in the plane XY. So now we would like to minimize the length in the plane XY for the front wheel. We are looking for the shortest path of the front wheel of the bicycle. This is the problem called F, the problem for the front wheel. But what problem do we have for the back wheel? We call this problem B. For the back wheel, the state space is once more, it is SE2. It consists of triples XB and YB. It is the back wheel, and theta B is the orientation of the back wheel. So we have the state space R2 times S1. And we have this control system, which we have already seen before. XY move in direction theta B with arbitrary linear velocity UB. And theta B dot is also arbitrary. We have boundary conditions, and we have Sub-Riemannian length, which is equal to the length in the space x, y, theta. This should be minimized. This is the problem B, which is exactly the Sub-Riemannian problem on the group SE2, which we studied before. So for the back wheel, we have the Sub-Riemannian problem on SE2. But what is it relation with the problem for the front wheel? Naturally, there is an isomorphism between the problems B and F. Here are the change of coordinates and change of controls, which transform one optimal solution to another. But physically, this is trivial. We have motion of a bicycle, which can be projected to a front wheel or to the back wheel. We have just two equivalent projections of one problem for the bicycle, projection to the front wheel or projection to the back wheel. But these two sides of the problem are very interesting to study and to compare. So what is the correspondence between solutions to the problems F and B? This is an example. You see that let's stop. The blue line is the line along which the front wheel moves, and the red curve is the curve along which the back wheel moves. So if the front wheel moves along a line, then the back wheel moves along this red curve. Let us see what is this curve. So here motion forward, and now motion backward. Of course, first it moves along the same curves, and then we see that the red, of course, the blue line is a straight line, and the red line is a tractrice. So if the front wheel of the bicycle moves along a straight line, then typically the back wheel moves along a tractrice. This is a correspondence between trajectories of the back wheel and the front wheel. But we already know all trajectories of the back wheel. Tractrice was one of the of projections of geodesics. Tractrice we know. And what are the possible motions of the front wheel? Of course, straight line is possible. But what are other possible motions? I mean, optimal motions of the front wheel. And there is a remarkable theorem and a relation to another remarkable family of curves called Euler elastica. The following theorem, the theorem is the following one. A projection XF YF of a geodesic for the problem F is either a straight line, which you already know, or a so-called non-inflectional Euler's elastica, etc. I will return to the theorem. Here is the picture. This picture shows you the family of Euler's elastica. Euler elastica is a configuration of an elastic rod in the plane with fixed endpoints. If no force is applied, then it is a straight line. If small force is applied, then we obtain a curve like a sinusoid. It is infinite and periodic. Then it becomes curved more and more. Then there is a remarkable elastica in the form of figure 8, and then it moves backward. This family of elastica all have inflection points. You see that here there are inflection points. Then there is a critical Euler's elastica called Euler's soliton, elastica with just one loop, and then there are non-inflectional elastica without inflection points, and in the limit they tend to a circle. So this one parameter family of curves that connect a straight line with a circle. There is a critical Euler's soliton which separates inflectional elastica from non-inflectional ones. And this theorem states that optimal paths of the front wheel of the bicycle are either a straight line, this one, or a non-inflectional Euler's elastica, so this one, including Euler's circle and Euler's soliton. And moreover, any form of non-inflectional elastica is possible. So these are optimal motions of the front wheel of the bicycle, Euler elastica. This family of curves, as everybody knows, goes back to Euler's work of 1744. In fact, it was the first treatise of Euler on calculus of variations. Euler created his theory of calculus of variations, and he applied this new theory to this remarkable problem, and he described all qualitative types of curves. You see, here is elastica in the form of figure 8. This is a sketch from Euler's book. This is inflectional elastica. This is non-inflectional elastica, and this is Euler's soliton. Euler did not describe parameterization of these curves because they are parameterized, as we can expect, by elliptic functions, which were not known to Euler. But he studied differential equations, and he described qualitatively the different solutions to these differential equations. So since that time, these curves are known as Euler elastica, and they appeared quite remarkably in our Sub-Riemannian problem. Now, several more words about Euler elastica. There are different definitions of them. First definition, I mean mathematical definition. Physically, as I have said, Euler elastica is a stationary configuration of an elastic rod in the plane with fixed terminal points and tangent at the terminal points, at the boundary points. But mathematically, there are several equivalent definitions. Definition 1, elastica is a planar curve whose curvature is a linear function of its distance to a fixed line in the plane. So this second definition, elastica is a planar curve whose curvature satisfies this second order nonlinear differential equation. And definition 3, elastic is a curve xy that satisfies this system. In fact, the definition 3 for me is the most geometrically obvious. So the point xy moves in direction theta, and theta satisfies the equation of pendulum. So the velocity vector of the elastica satisfies the equation of pendulum. This is one of the definitions. Great, and a remarkable property of this Sub-Riemannian problem is the following one. Consider the map denoted by phi, which flips the bike frame about the back wheel. So this is a picture. This is the back wheel. This is the front wheel. Their distance between them is equal to L. So this vector from B to F, initial position of the bike. And now we flip the bicycle, so the back wheel remains the same, and the front wheel flips to the opposite direction. And consider this mapping phi. And this lemma says that this mapping of our configuration state is a global Sub-Riemannian isometry of this space. So it if we flip the bicycle, then we map Sub-Riemannian minimizers to Sub-Riemannian minimizers. So this is quite geometrically visible. And now this is example how a straight line is flipped to Euler soliton. You see that this blue line is a straight line. It is the front, the path of the front wheel. The red Euler's soliton is the path of the back wheel. And if you flip the front wheel to this point, then we obtain a new blue curve, which is an Euler soliton. So this flipping mapping, once more, it maps straight blue line to the blue Euler's soliton. But what can we say with respect to optimality for the straight line? If we recall the problem for the front wheel, we minimize the length in the plane xy. So the motion along straight line are optimal, and the flip is a Sub-Riemannian isometry. That's why the blue line, the blue Euler soliton, is optimal as well. So from optimality of the straight line, we obtain optimality of the Euler's soliton. In fact, this optimality also follows from our old analysis of infinite geodesics. We know that Euler soliton, we know that track trees is an infinite geodesic. That's why Euler soliton is optimal as well. But now we obtain one more and geometrically more visible proof that Euler's soliton is an infinite geodesic. What are in general infinite geodesics for the problem F, for the front field? And there is the following theorem. An infinitely long bike path is an infinite geodesic for the problem F if and only if it is one of the following two types. One, its front track is a straight line and its back track is a track trees or a straight line. So the front path is a straight line and back path is a track trees, or it can be a straight line if the bicycle is aligned along this straight line. Or two, its front track is an Euler soliton and its back track is a track trees. So this is the front track is Euler soliton and back track is track trees. Moreover, there is an isometric involution of the bicycle configuration space, which takes path of one type to path of the other, which this we already showed you. This is the flip mapping phi. And the two infinite minimizing bike paths share the attractrix, the red line, as a common back track. The two front tracks are the straight line, dash blue, and Euler soliton, solid blue. So this is description of all infinite geodesics. In fact, we know that these are infinite geodesics. The theorem says that there are no other infinite geodesics. This we know. Then one more new result is description of the group of isometries. Here is the theorem. The group of isometries of our configuration space is an extension of the group E2 of Euclidean motion by the two-element group Z over 2Z, that is Z2. The two-element group Z2 is generated by the isometric involution phi, which flips the bike frame. So the group of isometries is the semi-direct product of E2, that is the group of all proto translations, both preserved and non-preserved orientation, with the group Z2 generated by flips. And the identity component of this group is SE2, is our state space. This was proved. Great. Now, one more new result on so-called homogeneous geodesics and geodesically orbital spaces. One more definition. A geodesic gamma in a Sub-Riemannian manifold M is called homogeneous if it is a homogeneous space of a one-parameter subgroup in the group of isometries. That is, we have one parameter subgroup phi s in the group of isometries, and for any s in R, phi s of gamma belongs to gamma. In fact, it is equal. And for any points G1 and G2 in gamma, there exists S such that phi s of G1 is G2. So, in other words, gamma is a homogeneous space of some one parameter subgroup in the group of isometries. Then the geodesic gamma is called homogeneous. And a Sub-Riemannian manifold is called geodesically orbital if all its geodesics are homogeneous. So this is a special class of Sub-Riemannian manifolds, geodesically orbital space. These notions are related to so-called equioptimal geodesics. Two more definitions. Let Q of t be a geodesic. An arc Q of t where time t varies from 0 to t capital is called a non-extendable minimizer. If it is a minimizer, but any arc at a segment from 0 to t capital plus epsilon is not a minimizer. So any segment which is longer gives you a non-minimizer. In other words, t capital is equal to cut time along the geodesic. This is a non-extendable minimizer. And one more definition, an arc-length parameterized geodesic Q of t is called equioptimal if it satisfies the following property. If Q of t, where t from 0 to t capital, is a non-extendable minimizer, then for any tau real, the geodesic Q of t plus tau on the same segment is also a non-extendable minimizer. So we can translate non-extendable minimizers along the time axis and obtain once more non-extendable minimizers. Then the geodesic is called equioptimal. And finally, a Sub-Riemannian manifold M is called equioptimal if any its arc-length parameterized geodesic is equioptimal. Why is this important? Because in all examples of Sub-Riemannian Lie groups, we have equioptimality. That is, consider left invariant Sub-Riemannian structures on the Heisenberg group, on the groups SO3, SU2, SL2 with axisymmetric matrix, on SE2, which we are studying today, and SH2 of hyperbolic motions of the plane, on so-called angle group, which is a four-dimensional nilpotent Lie group, and on Cartan group, five-dimensional nilpotent Lie group. In all these cases, the Sub-Riemannian manifolds are equioptimal. In other words, all left invariant Sub-Riemannian structures where the cut time is known, all these Sub-Riemannian structures are equioptimal. Why? In fact, nobody knows. There is no answer to this remarkable property of equioptimality. Although there is the following simple proposition. If a Sub-Riemannian geodesic is homogeneous, then it is equioptimal. So homogeneity implies equioptimality. What can we say about these properties in the case of SE2? In the case of SE2, we have the full description of homogeneous geodesics theorem. The only homogeneous geodesics in SE2 are one-parameter subgroups that are geodesics. The one-parameter subgroup corresponding to x1, that is, this is motion of the car forward, and one-parameter subgroup corresponding to x2, rotation of the car around itself. all the rest geodesics are not homogeneous. That is why SE2 is not geodesically orbital, but as we know, it is equioptimal. So it is an interesting question: why is a Sub-Riemannian manifold that is not geodesically orbital, why it is equioptimal? This question for SE2 remains open. Although the following D groups are simultaneously geodesically orbital and equioptimal: the Heisenberg group, SO3, SE2, and SL2 with axis symmetric metric. And there remains an open question: what is the geometric reason of equioptimality in the non-geodesically orbital case? This is the question we would like to answer in the future. Okay, this is the end of the news story, and now I will pass to some applications. Well, we have started from one obvious application to robotics. The Sub-Riemannian problem on SE2 is stated as a problem of optimal motion of a car in the plane. Another quite remarkable application is application to imaging, to anthropomorphic restoration of images. Suppose that we have an image in the plane which is decomposed into a family of curves. And suppose that consider one curve AB, and suppose that this curve is damaged somehow, and we would like to restore the arc CD in an anthropomorphic way. Anthropomorphically, in the sense that similarly to the way a human mind does it. What data do we have? We have terminal, we have boundary points CD, and we have tangent TC and TD. We have tangents at this point. We would like to restore the curve CD by this boundary data. We would like to restore it as a red line and then to place it instead of a damaged curve. This is our approach. And how this can be done? This can be done via the following ideology of so-called neurogeometry, which states this problem of anthropomorphic curve restoration as a Sub-Riemannian problem on R2, not S1 but R2 times RP1. This I will describe later. This approach is due to Jean Petitot. Here are two his seminal papers of the beginning of this century, and these
Юр, простите, это вот тот самый Петито, который занимался геометрией зрения?
Да. This is exactly Jean Petitot, and in fact, these are the papers of Jean Petitot about neurogeometry, where he stated the model of vision as a Sub-Riemannian problem. It is exactly that, Jean Petitot, yes. And Jean Petitot stated that the human mind restores damaged curves by solving the following variational problem. The curve in the plane XY should be a solution to the same control problem that we had before, and the functional should be also the same as we had before. So our mind restores curves in a lazy way, in the way that so as to minimize the energy of neurons necessary to restore the curve. And this energy of neurons is equivalent to this Sub-Riemannian functional. So this is one of the statement of the neurogeometry. The only difference with other problem is that now theta takes value not in S1. I recall that S1 is the segment from 0 to 2 pi, but now theta takes value in the segment from 0 to pi. That is, theta describes not a tangent vector, but a tangent line. but this is not very different. So in fact, how do we solve the problem stated by Petitot? Suppose that we have two boundary points and two tangent lines. Fix tangent vector at initial point and choose two different tangent vectors at terminal point in one side or in the opposite side, and find optimal curves for our Sub-Riemannian problem on SE2. This red one optimal curve for these boundary conditions, and this blue curve optimal for this boundary condition. Then we put them together and find the one which is better, and then we obtain the solution to Petitot's problem. So if we know solution to our Sub-Riemannian problem on SE2, then we can compare two solutions and find the best of them, and this will give us a solution to Petitot's problem. And so we have software for solving Sub-Riemannian problem on SE2. That's why we have software for Petitot's problem. This was done, and these are examples of curve restoration. You can see that this method feels quite well the curvature. This curve has inflection point. Somewhere inside this curve is convex, and in both cases the red arc is the restored arc. You can see that it fits quite well. And although there is one problem, the problem of is that the optimal curves can be smooth, which is okay, but they can in some cases they can have cusp points, as we know, which is not very good for image restoration. This problem remains, and we have some ideas how to deal with this. And my students designed software which restored damaged images, not natural ones, but artificial images. In fact, we took just a family of level curves of some function. We corrupted it in some domains, and then we reconstructed the curves. And you can see that here is the initial family of curves, isoforts, and here is the restored. And I think that difference cannot be visible. And here you can see the red elliptic domain where the isoforts were restored. Sorry. So you can see. So in general, this approach works quite well. Although, of course, there are some problems. One problem is that there can appear cusp points, and another problem is that, of course, natural images are hard to decompose into isoforts. In this case, this approach have to be developed. This was done by our colleagues by solving certain PDEs and non-holonomic diffusion. This was done, but this is far from our results. So here I think I will finish, and so these are our publications on the subject. The first the first three are old results of roughly 10 years ago. This is optimal synthesis of the Sub-Riemannian problem on SE2. And the two last papers are very fresh. One, paper 4, was just accepted by non-linearity, and paper 4 on homogeneous Sub-Riemannian geodesics is still being considered in a journal. So to finish, let me recall the main parts of this talk. We considered a simplified model of a car in the plane, and we consider a natural variational problem. We were looking for optimal motions of the car in the plane. This is an optimal control problem and simultaneously a left invariant Sub-Riemannian problem on the group SE2 of motions of the plane. We have described optimal synthesis, and we described a relation of this problem to the bicycle mathematics and to Euler elastica. And this problem, in addition to obvious applications to robotics, has also important applications to imaging. This I also tried to explain. So thank you, and here I stop. Thank you very much.
Thank you, Yuri. It was quite interesting. So questions, remarks are welcome. Please. No question, no remarks? Okay, Yuri, thanks again a lot. Next time we meet in the independent university, but the session will be broadcasted in Zoom, so everyone is invited the same time, the same day. So thank you for being here. See you next Wednesday. Goodbye.